So we continue on the basic combinatorial techniques, and today we'll start counting. Okay. So I think some more to type. So one of the basic problem that you can see in many places in combinatorics, that they want to prove the cardinality of two finite sets are equal. To show the cardinality of two finite sets for Y are. So this meta problem will arise in many contexts, and one of the interesting ways to show this thing is to set up a bijection. Set up a bijection f from x to y. If there is a bijection, then the cardinality of the two sets are same because there is a one corresponding. And I think all of you know, I just quickly refresh what is a bijection. That f is injective, two properties should be satisfied, meaning that for all x1, x2, x1 is not equal to x2, x1 not equal to x2. And second point is that f is surjective. What do I mean by that? That means everybody has a pre-image. For all y, there exists x such that x equal to. It's intuitive, and this picture can help. So that means if you have a bijection, you just pair up with the candidates. Okay. So I think all of us know it. So let's start some basic examples. Many examples that I will show today, you can prove this problem using other ideas, right? Ideas from calculus, or ideas from binomial theorem, ideas from multinomial theorem. But here we mostly focus on techniques that involve not many calculations, rather like a combinatorial argument. Sometimes these problems could be very easy, like you will see some of the examples. Sometimes they can be quite tricky. To find a combinatorial argument to prove certain identity or two sets are equal size could be tough. At the same time, I should remark that there are many problems in combinatorics. If you attack it via calculus, for example, let's say, then it could be very easily proved. But sometimes the teacher will ask you to give a combinatorial proof. Yeah, and it could be difficult to find a combinatorial proof. Once you find it, you will be excited. It's much beautiful than usual proof of calculus. Of course, it depends on your test. Yeah, so this is just a remark. For example, it's a absolutely basic example. So let's argue that number of all subsets. Okay, so this notation box n usually denote 1 to n. Okay. Number of all subsets of n is 2 power. We all know that this is true. This we have seen from our school days. But let me illustrate it via this principle of counting from two sides. That's the goal of today's lecture mostly. So let's say S is a set. Rather, I can write any set like A1, A2, AN, and I arrange a space. People who have seen programming, this I just simply call array. So this array of length n, and there is a box here, and this box you can fill up with either 0 or 1. So if I give you this kind of a string, so this string is a member of 0 on power n, and once I give you this w, you can define a set is w associated with w. It's very simple. SW is AI such that the ith entry of the string w is 1. Okay. So the w is really the characteristics vector of the set SW. And you can immediately say that these collections of all such w and collection of all such SW, this is a bijection. You can go back and forth from one to other. And this, since the cardinality of this side is 2 power n, cardinality of this side is also 2. So this is a very intuitive argument. And there will be a situation when this argument will be refined and could be difficult sometimes. Okay. It's like, for example, I'll give you two complicated looking expression and I'll ask you to prove that they are equal. I will not give it in the exam, but this is the task. Probably I should say that there is no rule of this game. How do you find these combinatorial arguments? Sometimes you can spend days in finding a combinatorial argument. For example, if you heard about this great book by Stanley, the enumerative combinatorics, there are problems that Stanley asks you to find combinatorial proof that can take few days, even one problem, if you don't hit the correct argument. These are very difficult problem. But how do you find a combinatorial argument is like a mystery. It is your ingeniousness, your intuitive ideas, and your practice, basically. There is no other, I don't think there is any other way one can set a rule that how someone will find a combinatorial proof. From calculus, calculus is more like a systematic approach. Many proof we can find in a systematic way. But these combinatorial proofs are often ad hoc. Okay, so let's take another example. Let's prove that this n choose k. I am not revising this basic permutation combination because I think all of you are good and you have done it in higher secondary. So this is the thing. This can you of course you know from your school days, and there is a one-line combinatorial argument for it, which is also very simple. For every set S of n of size k, you can associate T, which is S complement of size n minus k. So that's the association. That's the bijection. And the left-hand side counts the number of subsets of size k, and the right-hand side counts the number of subsets of size n minus k. There is a bijection. They're equal. Okay, so let's take a bit slightly more involved example. This is more like a story. So Alice is a medical student, and she wants to work in a lab for 5 days in the month of January. But she's not allowed to work in consecutive days. Okay. So, in how many ways? This is the question. In how many ways Alice can uh, have, or rather can plan and work days? This is the question. Okay. Is the question is clear? Question is very simple. January has 31 days, and Alice wants to work 5 days. No days are consecutive. How do you? How many ways Alice can schedule her working plan? Okay. So there one could, of course, have many ways to attack such problems. Probably you have seen such problems. So here we'll do one way that will help you in many other combinatorial proofs. Okay, so what is Alice trying to do? She's trying to find days. So let's say they are A1, A2, A3, A4, A5. These are the days in January, and no two are consecutive. Okay. And let us assume that this is the increasing order. So what is the requirement? The requirement is that A2 should be at least one more than A1. They are not consecutive. Right? So A3 should be one more than A2. A4 should be one more than A3. A5 should be one more than A4. This is the requirement. Right. So from the first, you know that A1 is A2 minus 1. Right? And also A2 from the second one is less than A3 minus 1. So A2 minus 1 is really less than A3 minus 2. Right? This is less than A3 minus, sorry, A3 minus 3, which is less than, sorry,
A4 minus 3 and A5 minus 4.
and this is A5, the writing is becoming 2. Right? It's very simple. And also you know that this A1 is at least 1 and they are bounded by 31. So this is 1 and this is 31 minus 4, so this is 27. That means if we pick any 5 element subsets from 1 to 27, this will give a sequence of bits for Alice, which is a valid schedule. Why is that is clear, right? So because if you choose some C1, C2, C3, C4, C5 from 27, you can think of like this is like increasing order. Then you can select your A1 to C1, your A2 minus 1 to C2. So your A2 is basically C2 plus 1, and so on. Right? So this is clearly a association or a bijection. So the number of ways 27 choose 5. Yeah. So I am not saying this is the only way. There could be many other ways to solve this problem, but this is an illustration of this technique of setting bijection between two different things. And when you write these things in your assignment or exam, don't write too much. Just give the crisp way, express your thought, how you argue this bijective proof. From my experience, I've seen some students try to write pages after pages to illustrate that this is a bijective argument. Many times they are correct, but checking those things in this online fashion will be very difficult. So you write in a very precise manner. Don't write unnecessary. Okay. Everybody followed this argument? Is there anybody who has some doubt?
So you have written A1 is equal to 1. A1 is greater than equal to 1, right?
Greater than equal to 1. Did I write equal to 1?
Yes,
No, I
sir.
write
No, sir.
yeah. You probably meant that, right? Oh, good. Okay, so this was an interesting problem. This was problem number 3. So there is a nice generalization of this problem, which is useful in many problems, like involving polynomials that we'll see later. So let me just write that problem. So count the number of k element multiset of it's somewhat in this language, but I want to illustrate it like a different problem. So this is the problem. Count the number of k elements multiset of 1 to n. So what is a multiset? Multiset means the elements can repeat. For example, this set, let's say 1, 1, 3. This is a multiset. It's a 3-element multiset. So how do you attack such problems? Yes, Aditi.
Yes, sir. So we could add some dummy like equal to symbols
Right.
to this set and then just choose k.
That's right. It's in the along the similar line that we just discussed, right? we can space them apart and see what is the problem. Problem is that they can repeat, right? And that's a bit tricky situation to handle. If there was no repetition, we would be very happy. We'll just prove like an choose our argument, right? That's very simple. So our some I mean intuitive goal will be to reduce this problem to a problem of picking what Aditi just said, probably that just from a situation where you want to pick R element from M element, where M and R you can manufacture depending on your question. Is that what you tried to say, Aditi?
Yes, sir.
Okay.
So we'll have n plus k minus 1 choose
Right.
k.
Good. She already told the answer. So I'll just illustrate it in a more systematic way, what she just said. See, we are slowly building. So we are still in the very basic level of the course. It is not like our entire course will be very simple. So I'm just building up things slowly from the beginning. So
So
we'll
can
have,
we say that we have k places, and since repetitions are allowed, so we have n choices for each place. So
but I want to, I understand what you are saying, but I want to illustrate in the way we want to do here. This bijective counting.
okay.
Okay, so that these ideas sink in our mind, and when harder problem comes, we can adapt easily. That's the reason I'm doing it. Yeah, you're right. This can be done in various ways. So just as before, let b1 b2 bk element and without such nullity. Yeah, these examples may look very simple and silly at the moment, but this warning is there that this finding bijective proof could be sometime really hard. So we want to spend some time on developing these concepts in mind. Okay. Right. So now I'll do what Aditi suggested, that let me space them apart so that there is no collision. So I'll associate this. Just use a different color maybe. Let me associate this sequence with this number. So this is a bijection. Using the same ideas in the problem we just discussed. And this goes up to n plus k minus 1 because I added k minus 1. So that means you have to choose a k element subset from that n plus k minus 1, and then we can have this association. This argument is very similar to the problem now. So, k element. Good. So argument is exactly similar. Okay. So good. So let's take another example. So example of slightly different test. Again using numbers. So let's count number of 5 positive integers. Integers containing the number 9 and divisible by 3. So, two conditions. Can you try it and tell me whoever solved and tell me the answer? I deviated a little bit. This is not exactly like a bijective counting. It's sort of implicit, not like the examples on top. Try to count. Whoever can count fast, tell me the number.
3,000.
Sorry?
3,000.
No. How do you get that? 3,000 is the number of numbers divisible by 3, just right?
3333.
3333. No. How do you get that? 3. You said 4-3, right? 3.
Yes.
No. How do you get it?
So when you say 5-digit numbers, is the leading digit allowed to be 0?
No, that is not a 5-digit number. It's a non-trivial, or rather, by 5-digit number we mean that the leading one should not be 0.
One 8,333.
Say it again. Sorry,
18,333.
No. How do you get that?
Well, 3 into 5.
1 minute. Tell it again.
3 into 5.
3 into 5. That's what you're saying. Are you saying that?
Yes, sir. Yes, sir.
3. The last digit is, your last digit will be 5 then, right? No, that's wrong.
15333.
1533. No. Rohan, I thought you were thinking the right track. Do you have an answer?
I don't want to just calculate it. I want to find a good way. Like I can see how calculation would work, but I don't want to do that.
Okay, good. But it's not a very long calculation. Some calculation is necessary, I guess. You cannot get rid of all the calculations. Yeah, but if you just suggest the steps, that would be excellent. No need to give the final.
I mean, one thing I could see is like if I start with the digit 9, then like I could recur in some sense, but that is just bad. Like I could recur in some sense, and I could say like mod 3, what is the thing, and roughly all are equal basically. So it should be fine, but that doesn't sound optimal.
I think someone has written something in chat. 1 minute. Soham, is it 2 power something you wrote?
Sir, that's actually a typo. The
Okay.
2 power just delete it. Wait.
Is the number is the answer of someone is asking a complicated question. Is the answer of the number of 4-digit number divisible by 3 times 5? I do not know. I didn't check it that way. Soham is writing 2 times 9 cube. So what is the last digit of your number? 9 cube means it is 9. Right. Can you just quickly calculate? So 9 is 81. 81 into 9 is 729, right? 729 into 6. What is that?
Sir, can we do a recurrence this way, where one case
Avoid recurrence. We haven't done it yet. So
So,
yes.
So we know the total number of 5-digit positive integers, and we know the number of integers that contain 9, like we can calculate that. But that is where it isn't nice. Oh, also we know the number of 5-digit numbers divisible by 3, so we could do the
Yes, and you have to do an intersection, right?
yes, sir.
So that's the. I'm curious to know Soham's final calculation. So 3 into 2, 6, and 729. What is 729 into 6?
Sir,
Yeah, I think it is not probably correct. Yeah, I think Soham probably understood it. No, it cannot be that big. Okay, so I think all of you, particularly I think Sohan and Aditi, got it almost like the way they were thinking. We have to.
so just
Yeah.
so just a minute. So please wait for a minute.
See, sure.
Sir,
Sir, could I suggest an idea for them?
One by one. I think Rohan is telling something.
So, is it 15,334?
15,334. No, little bit over count.
Sir, is it 15,329?
No, last digit is not 9. So Romit, 10,504. Close, yes. Maybe you undercounted somewhere. Okay, so this was just a fun. I mean, there is nothing like that we have to solve it now. Okay, so all of us tried. That is good. So it's this question is a bit tricky than the earlier problems, right? Ram is saying something. Ram, are you saying something? No.
No, sir.
Okay, good. No problem. Yeah. So,
Sir, I don't know why it didn't work. Can I share the idea? What?
Vijayan, you can do it offline because I don't have too much time. Then I will not be able to cover the other things. So I know that most of you will be able to solve it offline. There is no problem. Just let me just implement the steps that Aditi was suggesting, like count and try to take the intersection in a slightly different way. Okay, so let's do the proof.
So, sir, does this have a bijective proof? Or
Not really. This is just I picked up one of the problem to. You are right. It's not exactly bijective. Yeah, I'm just mixing a few things as we go on to make it more interesting. Yeah, probably using recurrence you can solve it, but since we have not done recurrence, let's do it from the first principle. So number of 5-digit positive integers. So as Rohan said, that first digit has to be non-trivial, right? It cannot be 0, the leftmost digit. So the number of 5-digit positive integers, how many? The leftmost can be chosen in 9 ways, right? And the rest can be chosen in 10 ways. right? So this is 9 times 10 power 4. Yeah. So among these, how many divisible by 3? That's very simple. One third, right? Yes, one third will be like among these 3,000, this is 30,000 basically, will be divisible by 3. So we got one thing. Now we want to intersect. I think Apratim got it. Yes, it is that 12504, right? Yes. So in these numbers, I want to intersect it with the things that contains 9. Okay. So let us count. In this means in these 30,000, the number of numbers which do not contain 9, then we will simply subtract from it. So what I am trying to count, you have this 30,000 number which are divisible by 3. Among these, I want to count the number of numbers that does not contain 9 anywhere. Then I will subtract it from 30,000. How do I count that?
That should be 8 into 9 to the 4 upon 3.
8 into you are almost there. Is it 9 power
9 to the
4?
power
You think?
4, I think.
9 to
4
the 4. 8 into 9 to the 4 upon 3.
4 or 3? Just be a little bit more specific. Because one digit, final digit, you have to adjust according to the module. Your
Right.
idea is correct.
8 into 9 to the 4, sir.
Excellent. No, 9. Why 9 to the power 4?
So you
One-
have to divide at the end by 3, right?
Right. That we have to ensure, right, that you are counting from this set finally.
Sir, 8 into 9 power 4 is the exact number of numbers without a 9. Since it is divisible by 3, we can just divide it by 3 so that we get the exact number of numbers which are divisible by 3. So
Right.
that's what
Right.
I think Rohit was saying.
Okay. I could not hear you properly. So what you are saying, like, so that means in the way I am counting it, it is 8 times 9 cube times 3. Is that what you are saying, Rohan?
Yes, sir.
Okay. Sorry. Yeah. Okay. So could everybody understand why it is like that?
Yes, sir.
Yeah, I think you
One
must have
second,
understood, but others, anybody has a doubt? Let us just do it.
Yes,
So
I did.
this is our number 1, 2, 3, 4, 5, right? So this can be counted in 8 ways, and this can be counted in any of these things can be counted is 9 ways, right? And so this makes you 8 times 9 power cube, and after that, when you add, you can get modulo 3. We can get either 0, 1 or 2, right? Now when you get 0, since the sum has to be divisible by 3, your allowed thing will be 0, 3, 6 for the last digit, because 9 is not allowed, right? When you have 1, your allowed thing will be 2, 5, 8, right? When you have 2, you have 2 plus 1 is 3, so it will be 1, 4, 7. That means after you do this, the next number will be picked in 3 ways according to your module. So this is like 3. So and now so this is some number, and if you subtract this number from 8 9q into 3, I think you get exactly what Aprotim wrote. Yeah, you are right. This is nothing to do with the context that we are doing. I just went a little bit in off direction and did one interesting problem. Okay, so let's now come back to our main thing on the combinatorial proof. So everybody happy with this example? Clear? Okay, so this is more like a tricks involved, but let's return to the combinatorial proof. So let's try to see this identity. So all of you know this binomial theorem, right? We have studied in 10+2 binomial theorem and its extension, which is multinomial theorem. And probably you have done much more than what I know by solving lots of problems and identities. You can take any textbook from your 10+2 and look at an identity and wonder why this identity is true. Most of the proofs that we have done in our 10+2, we use a calculation-based approach. We try to compute the powers of two things from binomial expansion and then do some calculus-based trick to differentiate, integrate. All these things generally we do. So here we don't want to do all such things. We'll try as much as we can to give proofs of many identities using just intuitive argument, not like long binomial calculation. So let's take a basic example. This identity we know very well from our college days. So let's see. So why this is true? Can somebody give a non-calculation based proof?
Yes, you have n+1 things. You just decide whether you choose the last thing or not.
Right. So this is probably we have done in our 10+2, right? So let's just write it. So okay, in exam when you write it little bit more formally so that we can understand that you got that bijective argument correct. Okay. So RHS is the number of k+1 sets from n+1. And let's analyze LHS. So the first one, so let 1 is, as Rohan said, I can fix any number. 1 is included in the set. Then the rest can be picked up in n choose KOs. This is the case 1 and case 2. 1 is not in the set. Then we remove 1 and pick the k+1 size set from the rest. Then the set can be picked up in n choose k+1. So we count the same thing, right? Because the right hand side has all the sets which may or may not contain the element 1, and left hand side we exactly counted them. That's the proof. So counting in a two different way. Okay, so let's take more example. So let's take let's solve this problem. K choose K, K+1 choose K. N choose K, that is equal to again the same number, n+1 choose K+1. Can somebody attempt? Not Rohan. Rohan has attempted already many things. Yeah. Try to solve this one. You can solve using any binomial kind of thing, but let's solve it using just intuitive argument, no calculation.
Sir, can we take k, choose k to be k plus 1, choose k plus 1, and then use the previous result?
Say it again, k.
Write the first term, k, choose k as k plus 1, choose k plus 1, and then use the previous result like continuously.
Choose. Sorry, can you just repeat once more? So you are saying k choose k plus.
So since k choose k is equal to 1, which is, we can write it as k plus 1, choose k plus 1.
This is what is saying, right?
Yes, sir. Then the first two terms.
Oh, you can merge one by one. That's the thing you are saying.
Yes, sir.
Yes.
Plus 1 choose k. So that will be, that will go to k plus. So that will go to k plus 2, right? K plus 2, choose k plus 1. Right. So you can continue like this. Okay. But that's not a combinatorial proof. Yeah, that's the correct proof.
So we can do like we have to.
That's right. I mean, whoever said, I think it's correct. You can just use the identity above. But is there any nice combinatorial proof?
Sir, like if there are n plus 1 elements, then first we keep the first element in the set, and then we take k elements from the n elements left. Then we keep the first two elements, and then we choose n minus 1 element, k minus 1. No, okay, it's wrong. No, it does. First the cases, it won't contain one element, and then you choose n elements. And the next one is it won't contain two elements, then you choose k.
But how do you get this sum by your argument? This nice sum are you getting in your argument? I cannot understand what you're saying exactly.
No,
I that you don't get the sum.
It's wrong.
Yes.
Sir,
So if n plus 1 is present, then nck. If n plus 1 is not present, then now out of the remaining possibilities, n could be present or n could not be present. So if n is present, then n minus 1 ck, and so on till k ck. So is that right? Like it will be the total summation. Like to put it in better words. To put it in better words, if we take,
it's like an inductively you are building, right? It's not exactly a combinatorial proof. Combinatorial proof means the expression given in the left hand side, you have to identify with a physical situation. So like a description in English. Right hand side, you have to define it another description in English, and these two descriptions should be equivalent.
Sir, for the left hand side, we can write as the sum of the coefficient of 1 plus x whole power t, where t sums over 0 to n.
That's not
coefficient
a
of x power.
I have a solution.
That's not a, so many solutions could be correct, but these are not exactly combinatorial.
Okay.
We want to choose our R plus 1 subset of 1 to 3 up to n plus 1. This is the RHS. Now we can count LHS in this way. We are considering an R plus 1 subset of n plus 1 in which maximal element is I plus 1.
Right. That's right.
So other elements are from 1 to I. So you have for each I you have choice I choose R, and now it sums over I.
Right. So for the k choose k, let's say the maximum element is k plus 1. Right. So you don't have any other choice. And this k plus 1 choose k, the maximum element is k plus 2. That's how you are saying, right? Yeah. So let me just write. Who said it? Ritabrata, right?
Yes, sir.
Yeah, I think most of you, nothing is wrong mathematically. I just wanted to manufacture a combinatorial argument. Combinatorial argument means, like the Bijan was telling, he was associating some more like an analytic idea, right? Some x power or something, and he was doing. Someone showed an inductive proof. Maybe most of the proofs are correct, but this RHS, it's clear. So what is a LHS? So to see the LHS, fix the maximum number of the set is k plus j, and choose k elements from k plus j minus 1. That is what we are doing, right? For example, this, look at the first term, k choose k. So if your maximum element is k plus 1, then you don't have any choice, only the k choose k. And the maximum element is k plus 2, then you have a choice of choosing k from k plus 1, choose k. If the maximum element is k plus 3, then you have choice k plus 2, choose k, and so on. And the maximum element is n plus 1, then you have a choice from n, choose k. So there is no induction, no analytic business. This is like a purely combinatorial argument. Okay, so everybody agrees? Like this is fine? Rohan, Aditi, is this what I said? Do you agree?
Yes, sir.
Okay, good. So others?
Yeah, sir, it's fine.
Okay. So example. So let's. This is really fun. This combinatorial proofs. Once you will like it after a few examples. So this is called. This is a famous identity. This is very simple. The combinatorial. Anyway, this is very simple because from the structure itself, yeah.
So may I say the argument?
Sure.
There are n girls and m boys in a class. You want to choose k of the students. First you choose I boys and then you choose n k minus I girls, and you're done.
That's right. See the advantage. If you have to do this, it's using this calculus. You have to set up this possibly like two things, and then you have to multiply and collect their common powers. Right. So here one gave like a one-line argument. It's very simple. You have n boys, right? N girls and m boys, and choose. And you have to take I students out of that. Select I girls among n girls, and select k minus I boys from m boys. That's. So, okay, so it's k times n choose k. This is also a famous identity, k equal to 1 to n. We all know how to prove it like analytic method, right?
Yes, sir.
So may I say?
No, not you, someone else. Yeah.
Sir, can I say?
Yes, someone else.
So we are forming a team of we are forming a team of n people, and we are choosing the we are choosing one captain. Okay.
Good, right.
So,
exactly. So now completely.
No, so we are forming arbitrary team. Okay, so like the number of members are arbitrary.
Arbitrary. It could be arbitrary.
But we have one captain.
Yes.
So the RHS is, first of all, we choose the captain in n ways, and then for other n-1 people, they have choice of remaining in the team or not.
Right. Choose the captain in NOS and rest in any order. Right. And the LHS, pick the team and pick the captain. Right.
Huh?
Pick the team and pick the captain.
Yes.
Pick the team and pick the captain. Okay, so let me make your life little bit interesting. I think people are finding it too easy. So k square n choose k n into n plus 1 2 power n minus 1.
So same
No,
argument.
no, I think you know all these proofs. Someone else, yeah. If
I mean,
others
you can
cannot,
choose
I
a
will come back to you. Yeah, Rishabh, yes.
like a captain and a vice captain. So on the right side,
Captain
you
and vice
choose.
captain. Yes, yes, good idea. Try.
So on the right side, you have n+1 people. So n+1 times
First,
n.
Rishabh, let me go step by step. So, from how many you are selecting your team?
Okay, n+1 will not work on the left.
You are almost there. It just more
Okay,
thought.
wait, yeah.
Think about it. You're almost there. See, here is a very simple proof from calculus, right? You take 1 plus x power n, expand it, differentiate, multiply by x, differentiate, put x equal to 1. You will get a proof. But I want a combinatorial proof, not via this analytic. That's also correct, what I just said. What I just said, everybody followed, right? Take the expansion of 1 plus x power n, differentiate, right? Then you get 1k in front of you, multiply by x, again differentiate. Then you get exactly k square. And then put x equal to 1. This captain and vice captain idea is correct. You have to just refine the idea.
So can I try?
Yes, Subramanian, tell.
So the right hand side, so I first choose the captain. So as English, now the same person can be voice captain or a different person can be voice captain.
Right, right. Although it is not true in football, but yeah. So in mathematics, it could be true. The same person can be vice captain or a different vice captain should be chosen. Good. So let's just complete what is said. True. So what is your team size? I mean, the global team size from where you are picking, this is n or n plus 1?
N.
N. So pick a captain from a team of n players and then.
So it needn't be the captain and the vice captain. So it can be the captain and the goalkeeper.
But the point is that there will be one place. Oh, you mean make the captain goalkeeper? Okay, that's a good idea. Yeah, you are closer.
So you said you use the analogy of captain and vice captain. I am saying that it needn't be captain and vice captain. We can have the analogy of captain and goalkeeper. The captain can also be the goalkeeper, right?
Right. That's what I said. Yeah, captain can be also the goalkeeper. Yeah. But since I wrote the captain, right, pick a captain from a team of n players and then pick a goalkeeper who can also be captain. Also be the captain already picked. It could be a different person also. Okay, so first assume the case is a captain is not equal to goalkeeper. Right? So what is the way? Pick your captain in n OS, pick your goalkeeper in n-1 OS, and you are left with n-2 players to choose from. So that can be selected in 2 power n-2 OS. Right? And then pick next consider the captain, the case where captain is the goalkeeper. So first thing, the captain can be selected in n OS. He will be the goalkeeper, and the rest n-1 among n-1 you can select a team in 2 power n-1, which is n times 2 power n-2 into n plus 1. And what is the interpretation of LHS? It's the same thing, right? You choose your team. Choose. Yeah.
So the power was n minus
Yeah.
2 in the question.
N minus. Sorry. I made a mistake. Oh, is that the thing you got confused with n minus 2? I made a mistake. Sorry, n minus 2. Oh, I hope that's not the reason people are silent. Sorry, I made a typo. So choose a team of K players and choose captain and goalkeeper with repetition. Right? That's the proof. Okay. 1 minute. Okay, just come back. Okay, so I think we have now 10 minutes. So let me just tell you this multinomial theorem. So what is multinomial theorem? It's, we know, right? So you have x1 plus x2 plus xk. It's a generalization of the binomial theorem and taking power n. And we want to write the coefficient. So what will happen if you expand this x1 plus x2 up to xk power n? X1 will get some power, x2 will get some power, xk will get some power. For example, a typical monomial will look like x1 power a1, x2 power a2, xk power ak. What is the coefficient of this monomial, you think?
N factorial by a1 factorial plus a2 factorial.
Right. So this symbolically I write, right. AK, where a1 plus a2 plus ak equal to n. And what is the meaning of this notation? Meaning of this notation is n factorial. It is a1 factorial. A1 factorial, a2 factorial, right, ak factorial. So now, Bijan, you tell me, like, how do you prove it? Like the coefficient of this monomial is this, what you just said.
So we have a1 of x1 and a2 of x2, then we consider all the permutations with repetition. That is
right.
That gives n factorial by
That's the, yeah. Now I give you one example. So let's prove prove the following. AB n A to B C equal to n minus 1 3 power n minus 2. Let's prove it combinatorially.
Sir, what does the notation mean? N choose A comma B comma C?
Oh, this means as I wrote, and repeat again, this is n factorial by A factorial, B factorial,
Oh,
C.
sorry, sir.
Same thing. No problem. You can prove in calculus.
So may I say the argument?
Yes, Rohan, tell.
So let's say you have 3 houses, red, blue, green house in a school with n students. You need to allot every student a house, but also red and blue house don't have a house captain. So
if student a house, and also say it again.
Every student you need to allot a house, but red and blue house also need a house captain. So
House captain.
yeah, just some position in the house, special position in the house.
Okay.
Like, so you just allot A students, B students, C students, and from the A students you allotted, you choose a special student, from the B students you allotted to that house, you choose a special student, and that's it. Or otherwise, you could have you have n choices for the first house captain, and -1 choices for the second house captain, and 3 to the n-2 to just allot the other houses.
Yeah, I think you're on the right track. But can someone illustrate in a more like a language of a string, colored string, maybe string colored with 3 things?
Okay, so you can say that you need to.
You're right. You're right. I just want someone else to catch that track that you suggested and explain it maybe in a string language. House is correct. I think you're right. Someone can attempt it. I think these things, like, they are so interesting. You can spend days and night doing this combinatorial. Don't do that, but it can happen. Like, it's like sometimes it becomes like your passion, finding a combinatorial. If you read the books by Stanley, this is the always suggestion: find combinatorial.
Sir, I don't understand how you want the phrasing in string manner.
So tell me.
I got the idea. I mean, I understood it in the same way Rohan did. We can think of it as there are n places, and we need to fill them with either 1, 2, and 3. But one of the ones is special, and one of the twos is special. And so basically, we choose one place with the special one place with the special two, and fill the rest of them randomly.
Or anyways, randomly is not a right thing. That brings something else in mind. But anyways, you means.
Yeah, yes, sir. So that will be n into n-1 into 3 raised to n-2. And and on the
I need more clarity. Aditi, you want to say something?
Can I?
So the example, like the kids wala example, is the only way I see it right now. In the sense, even if I state it in terms of strings, it would still be the same idea.
Sir, is the right side all possible 3 powers? Sorry, all possible ways of representing a number in base 3 with at least 1, 1 and 1, 0.
All possible numbers in base 3, 1, 1 and 1, 0. Right. And what about the left?
That I'm thinking, sir.
Okay. Right track.
So that wouldn't quite work.
Yes, Apratim, tell. Yeah.
Yes, I have a little different approach, sir. So there's a little analytical step, and after that we can apply a combinatorial argument.
Combinatorial proof should be 100% combinatorial.
So the 3 color string, we have 3 color with 3. I mean here, so I mean red, blue, green. We color the string and make something like 2, as he said, that 1 and 0 should be appear. So red and green should appear, and blue should be. So that makes the right hand side, and the left hand side we partition that like a number of blues or b number of will that be?
Absolutely, yes, you're right. Perfect. And little more, yeah, not perfect. Sorry, little more after that.
Sir, we can in RHS we can. So what are we doing?
1 minute. What Bijan said, the right hand side is perfect. Left hand side, he was almost done. One more line is required. Yes, Saptarshi.
Sir, so we are coloring with three colors, red, blue, and green. And among the red, we'll get one dark red, and among the green, we'll get one dark green. Then first we choose in RHS, we first choose the dark red and dark green. In any
Why don't you
one
three
way.
color? Why do you want to make my life complicated by saying dark and light? Why not choose just what Vijan said? Green. What are the color you choose? Green, red, yellow, right?
Yeah, green, red, blue, and just one of the green will be dark green and one of the red will be dark red, like that.
Do you need so much?
All the others will be normal green and red, I think. Then we can choose the RHS first, dark green and dark red in n to n-1 ways, and for all the others we have 3 times n-2, 3 to the power n-2 ways. And in LHS,
dark, light, these things are not probably required. You can make it simpler. Okay, so let's, I think most of you are correct. So I just make it more systematic. Okay, so you have, let's say 3 symbol, x1, x2, x3, and look at the right RHS. So RHS, these are the n places, right? Among n places, choose 1 and place x1, then choose another one and place x2. The rest can be filled up in any ways. This is what Vijan said, right?
So, but this won't work. You need to give the special property of the first x1 and x2 you're filling. You need to remember those places. It's not just that you're placing them. You also need to remember that I placed in this position and this position.
Why? But this is the count for the right hand side. What I just said.
Yes, sir. But like, if you're just in the end, if you're just leaving it at
Let me
like
let me just try. If I may be wrong, let me just complete. So this you agree, right? This can be like n minus 1 and 3 power n minus 2. Do you agree on that?
Yes, sir.
Okay, so let's now do right hand side. Okay, so sorry, left hand side. So for the left hand side, place x1, place x1 in a location among n locations, and place x2 in B locations among n minus a locations. Rest anyway. Then identify one special location out of A locations for x1 and out of B locations, out of B locations for x. Thank you.
So the argument everyone was giving was the same, just like the special locations you are saying was just
because
said as dark colored location.
Offline, it's difficult to understand so many things. I told her, right? Most of you are correct, but just make it more specific. Yeah. So that's all. I think So we may continue on combinatorics next class, or we can switch to some other topic. So we can, because there are two of us teaching, so we can either mix topics as we go on, like weekly, or we will decide and let you know, and or we can continue on combinatorics. Okay, I think there is. I should start for